Okay, so how is everyone today? Good, I hope. Any questions before we get to business? Yes? Well, let me finish writing this. 0226. So you have scans up that you can download. The ones you have some that are. So you have a look at the scans, and you also need to have a look at the calendar webpage to see which are out of 10. To see which are out of 10. Then the WEX part of your grade is you add up all of the ones that are out of 10. You add up whatever grade it is that you got. The ones that are not out of 10 are out of 1. You add all those up. That's 80% of your grade. The something I think 10% of your grade is the WebAssign stuff, and the other 10% is more or less whether or not you're turning in all this stuff on time and attempting all the homeworks and things like that. Other questions? So some other students from the other sections told me that they had some difficulties downloading some of the homework assignments. Did you all have some of those difficulties? Okay. I'll look into that this afternoon and figure out what it was that happened. Good. So any other questions before we get to business? Yes? Well, okay, no, that's a different matter. So what I was speaking of is these. So some students said that they had difficulty downloading that, and then so what you're speaking of is on the WebAssign. Some of the exercises required Adobe Flash. Yeah. So well, you got to install that thing. It's kind of a piece of junk in my opinion, but well, at any rate. So what's the name of those folks? The help desk. There's something called the UTD help desk. And they can help you do a variety of things, including to install Adobe Flash. If you can't figure it out on your own. It can be kind of difficult to figure out on your own, actually, because Adobe Flash is being phased out. So you've got to like click some buttons to say, yes, I want to use it actually in my web browser. Okay, other questions? Okay. So here we are. So if we say let A and B be in the reals, if that's true, then if the product AB is 0, then A is 0 or B is 0, and then when a mathematician says or, they mean or both. Which is different than like when you're talking to a child and when you say you can have cake or ice cream, and that means just the one or just the other, but not both. When mathematicians they say or, that means this one, that one, or both. Which raises the question, well, what does a mathematician say when they actually mean the cake or ice cream or, And in that case, you say XOR, which is XOR. Okay, so the way in which this is used is something like this. Please solve x squared minus 13x plus 30 is equal to 0. So the trick is to turn this into something like the previous remark, and that is if we could somehow turn the left-hand side into the product of some things, we'd be in good shape. So is it somehow possible to factor this? Yeah. How does it factor? Not quite. So the one that I heard was this, I think. X minus 15 multiplied by x plus 2 equal to 0. So is that one right? Right. So this one is sort of a little bit dangerous, right? Because it adds correct, the sum is correct. The sum is negative 13, but the product is not. Right? Because the product would be negative 30, but we need to be positive 30. So not this one. Rather, yes, I heard someone say it, x minus 3 multiplied by x minus 10 equal to 0. So what I want you to observe now is we've factored it, and well, what we're saying is that the product of two things is 0. So either the first thing that I'm obscuring is 0, or the second thing that I'm obscuring is 0. One of them must be 0. So either x equal to 3, x minus 3 is equal to 0, or x minus 10 is equal to 0, and then now both of these equations can be solved. So either x is 3 or x is 10. Any question about this one? Okay, so how about please solve. How about w squared plus 17w then minus 60 equals 0. So same trick, really. Okay, well, okay, good, except with w's, right? So then that would be w plus 20 multiplied by w minus 3 equals 0. Because 20 multiplied by negative 3 is negative 60, and 20 plus negative 3 is 17. So w plus 20 is 0, or w minus 3 is 0. So either the first thing is 0 or the second thing is 0, and then you can solve for w to obtain that w is negative 20 or w is 3. Any question about this example? Okay. So let's have a more exciting example. So this is me back in my office conspiring to make an exercise that's exciting. I'm going to make it exciting in the sense that, well, the two previous ones were monic, but let's make one that's not monic. So here's me making an exercise. So 2 times w minus 7 multiplied by 3 times w plus 8. If I multiply this out back in my office, then I get, what, 6 w squared, and then plus 16 w minus 21 w minus 56. So again, that's invisible. You pretend that it doesn't exist. So the exercise is, please solve 6 w squared minus 5 w minus 56 equals 0. And then you look at this one and think, oh great, this is going to be a fun one because it's not monic. What do I mean by that? Not 1, right? So then, like in this exercise, the leading coefficient was 1. It was 1x squared, and in this one it was 1w squared. But in this one, it's 6w squared. So it's not monic, which means it's going to be the interesting kind. Okay. So what we want is we want to find two numbers whose product is what? Well, we want it to be the product of the first and last coefficient, right? So 6 times negative 56. Which is negative 336. And what do we want the sum to be? Negative 5. Okay. So this is like a seek and find. Let's try a couple. Okay, how about, well, I'll just hope for the best. How about 6 and negative 56? Will that work? Nah, it's not going to work. How can you tell it's not going to work? Right, if you add those together, you get negative 50. And that's not what we're looking for. We're looking for negative 5. Okay, so that means because this number is, in a sense, too big, too negative, that means that we need to make the biggish one smaller and the smallish one bigger. Okay, so these need to be more similar in size. So, well, that means that one of the factors of negative 56, we need to transfer it to the other one. So I'm going to do it like this. Well, I see that negative 56 is even. So we could divide it by 2. What would you get if you divided negative 56 by 2? Negative 28. And that 2 can't just go nowhere. It has to go to the 6, right? So then what's 6 times 2? 12. So let's verify that we didn't make some kind of silly error. How can I verify that this is a legitimate pair? By multiplying them together and checking what? That it's negative 336, right? So 12 times negative 28. Negative 336. Okay, good. Add those together, and we get what? Negative 16, right? Okay, so is that the winner? But it's not the winner, but do you detect that we got closer to negative 5? So we're using the right kind of strategy. So negative 28 and 12, they're too far apart, so we need to, again, transfer something some way. So what do you want to do? How about, well, if 2 worked good one time, maybe it'll work good another time. Let's give, I don't know, let's give another 2 over to that one. Will that not, you don't like that? Well, we'll just do it just to see. So, negative 14, and then if we put the, if we give that 2 over to this one, what do we have? 24. Is the product still right? The product is still right. Now the sum is 10. Okay, so, well, we overshot it, right? So do you see that we went negative 50, negative 16, that's good, and then phew, way too far. We went to 10. Okay, so now what? I'd like to point out that the answer is obviously 16 and 21, right? that's what the answer is, but we don't know that, right? Because that's invisible. Well, what do you think? So it's not a 2, right? So now this one is too big. So we need to take something from this one and give it to that one. But it's not going to be a 2 because if we do it with a 2, we'll just be back where we started. So what else could we try? How about a 3, right? Let's take a 3 from this one. What if we divide this one by 3? What do we have? This would be 8 if we divide that one by 3, and then multiply this one by 3. Negative 42. Is that product still correct? Let's double check. 8 times 42. Well, I forgot the negative, but I'll remember it in my head. Negative 336. Okay, so that's still good. If we add these together, what do we have? Negative 36. Oh no, we're getting further. Is that right? 34. Okay, well, I'll try another 2, right? We made a 2 go that way, a 2 go that way, a 3 go that way. Now I'm going to make another 2 go that way. So if we divide this one by 2, what do we have? Negative 21. If we multiply this one by 2, what do we have? 16. And then we found it. Right? How do we know that we found what we were looking for? The sum is right. So to be clear, in a sense, to get from this one to this one, we made a 2 move from the right factor to the left factor. To get from this one to this one, we again made a 2 move from the right factor to the left factor. To get to this one, what did we do here to here? We moved a 3 from the left factor to the right factor. And then to get to the last one, we moved a 2. So, in a sense, we started out with the 8 on the wrong side, right? So 2, 2, 2, all those needed to go to the other one. But we found it in 5 steps, or 5 tries, 4 steps, I guess. Any question about that? So now that we've found 16 and negative 21, what is it that we need to do with them? Right. We're going to use these to split negative 5w. Because at the present time, there's 3 terms, 1, 2, 3, and we want to have 4 terms. And we're going to turn those 3 terms into 4 terms by causing this split. So that would be 6w squared minus 21w plus 16w and then minus 56 equal to 0. It doesn't matter how you split it. That is to say, I could have written the 16 first and the negative 21 second. That'd be fine. But the algebra ends up being a little bit easier if you write the negative one first. So I'll do that. Now, we have 4 terms. 1, 2, 3, 4 terms, which means that we can have 2 groups of 2. What do we do with each group? Okay, good. So in this first group, we want to factor out the greatest common factor. What is it? 3w. 3 because 3 is the biggest integer that divides 6 and 21, and w because that one is limiting. So 3w comes out. And when you take 3w out of that, what's left? 2w minus 7. Okay, then we want to do a similar thing over here. So concerning this group, what's the greatest common factor? 8. So 8 comes out. And when 8 comes out, what is left? 2w minus 7. And I'm feeling good about this now. Why do I have warm and fuzzy feelings? Right, these two are the same. If these were not the same, that would signify that an error has been made. So those are the same, and now what I want you to imagine is that, well, maybe here I'm covering up a y and here I'm covering up another y, which means that a y could be factored out, right? Because here's 1 and here's 1. So if we factor out the y, then what would be left is 3w plus 8. So we'd have 3w plus 8 multiplied by 2w minus 7 equal to 0. Any question about getting to here? And now we're in the same position we were twice before. We have the product of two things is equal to 0. So either the first thing is 0 or the second thing is 0. So 3w plus 8 is 0, or 2w minus 7 is 0. And so now, we were asked to solve one equation, and what we did is we said, well, instead of solving this one equation, I'm going to solve these 2 equations, but these 2 equations are simpler. So it's like breaking the problem into 2 simpler parts. So this one can be solved by subtracting 8. 3w is negative 8, or 2w is 7. And then this one can be solved by dividing by 3. W is negative 8/3, or w is 7/2. Any question about this example? Okay. So let's have an easy one. How about please solve z squared minus 1 is equal to 0. And again, I want you to solve it by factoring. Right. Very good. So you could write 1 as 1 squared, because 1 squared is 1. And then yes, now this is the difference of squares. And how does the difference of squares factor? As the product of conjugates, yes. So z plus 1 multiplied by z minus 1. The expressions z plus 1 and z minus 1 are said to be conjugates to each other because when you have something that looks like a plus b, its conjugate is a minus b. Okay, well, I'll skip to the end of this one and just say, well, either z is negative 1 or z is 1. Okay, so how about this one, which looks quite similar? Please solve z squared plus 1 is equal to 0. So it's literally the same question, except for one more pencil stroke to make the minus a plus. So how about it now? Can we? Is it possible to do the difference of squares thingy? Why not? Because it's addition, right? It's not a difference. It's not a difference. Won't work. I think you might have said, what if you do it like this, z minus 1 multiplied by z minus 1, if they were like this? Well, let's FOIL this out real quick. So the f term would be z squared, the o term would be minus z, the I term would be minus z, and the L term would be plus 1. So the first and the last would be good, but what? But these middle ones, that makes it not work. So that won't work. Well, I'm not sure what you mean, solve it as it is. Okay. If we move one to the other side, then it looks like this. So, here's the question. What z in the reals would do this? None, right? What if you squared a positive z? Would the result be negative 1? No. What if you squared a negative z? Like if you squared like negative 3. What's negative 3 squared? It's 9, right? No real is going to square to be negative 1. So there's no real. There's no real that will do that. Now, in history, most folks were completely satisfied with that, more or less. Like, okay, well, I guess not all equations can be solved. Okay, fine. But there were some folks who said, you know what? I want to imagine what it would be like if there was a solution. So, well, back in the day, right? Mathematicians didn't always exist as such, right? So, one of the most famous mathematicians, in scare quotes, of all time is someone named Isaac Newton. But in his day, he wasn't called a mathematician, right? Actually, in his day, there was the specializations of mathematician and physicist and chemist and all of that. Those weren't even made, right? So the title of Newton was actually natural philosopher. So that means that more or less at that time, physicists and mathematicians and scientists, they were all the same people. They were all called natural philosophers. Well, there was a group of natural philosopher folks who said, you know what? I want to imagine what it would be like if there was a solution to this. And then the people who more or less would be physicists said, no, we're not going to do that. We're not going to even imagine that. And if you do that, that's all just going to be imaginary and in your imagination. So the title of this remark is called the unit imaginary number. So we will define lowercase I to be a solution to z squared plus 1 is equal to 0. Now there's some immediate consequences to this definition. The first consequence is that I is not real. But understand the meaning of that. That doesn't mean that I doesn't exist. It's just not in the set that we refer to as the real numbers. So historically, again, going back to the history of it, this is a slight distortion and exaggeration of the history. But it's more or less like the folks who would be physicists said, that's just in your imagination. And the folks who said, no, I'm just going to go ahead and go with it. I want to know what it would be like. Those folks are the folks who became mathematicians, and they're the ones that got to choose the name. And the mathematicians retroactively renamed the set of numbers as the real numbers. Before that time, they were just called the numbers. Then these got called the real numbers. So I is an imaginary number. It's not real. Well, it is also true that I squared is -1. And furthermore, 3, negative I is also a solution to z squared plus 1 is equal to 0. Okay. So besides being able to solve the equation z squared plus 1 is equal to 0, what else do mathematicians use I for? What do we use I for? Well, we use the imaginary number to count our unicorns. It's a joke. Right? Okay. So, the set of complex numbers. The set of all expressions of the form a plus bi, where a and b are real, is called the complex numbers. And that set is denoted with a fancy C. In the same kind of way that the reals are denoted with a fancy R. Okay, so in English, the word complex has at least two meanings. One of them means difficult, and the other one means consisting of multiple parts. In this case, complex means consisting of multiple parts. Complex does not always mean difficult. So, for example, a shopping complex is not a region of space in which it is particularly difficult to shop. Right? It's a place where there's multiple places to shop. So, for such a complex number, a plus bi, the a is referred to as the real part, and the b is referred to as the imaginary part. So notably, it's just the b, not bi. So, for example, for the number 13 plus 14i, what's the real part? 13. And what's the imaginary part? 14. So a complex number is in a sense like, well, it's like a pair of real numbers. And we refer to those to the individual parts as the real part and the imaginary part. Okay. So, well, what if we wanted to add two complex numbers? So, like 2 plus 7i, and we want to add to that 5 minus, I don't know, 12i. Well, this works just like polynomials, which is to say that if you, in your mind, replace the I with just an x, and then add things together just as if they were polynomials, you'll get exactly the right answer. So you add the imaginary parts. So that would be, well, add the real parts, I mean to say. So 2 plus 5. Add the real parts together, and then add the imaginary parts together. And then simplify. So that'd be 7 minus 5i. And if we copied and pasted this and replaced it with x's, it'd be something that you could have done weeks ago. Now, what if we change the operation from adding two complex numbers to multiplying them? That's when it gets a little interesting. So, same two complex numbers, except now we're multiplying them instead of adding them. So, we're going to proceed just exactly with FOIL. So the F term would be 10. The O term would be negative 24i. In FOIL, the I term would be 35i. And then the L term would be minus 84 I squared. So now the terms in the middle, I'll collect them. So that'd be 10, and then watch, 11 plus 11 I minus 84 I squared. So far, what I've written, this is exactly like doing FOIL with polynomials, as if we had just replaced the I with an x. This is where you'd stop. But now we have to go a little bit further. Yes?
Didn't we write above earlier that I squared is negative 1?
Right. This is the further that we must go, and that is that yes, I squared. That's not a real. That's the imaginary unit. What is I squared? It's negative 1. So this would be 10 plus 11i, and then minus 84 times negative 1, because I squared is negative 1. Okay, so that's not really subtracting 84i squared, that's really adding 84. That's what that really means. So we're going to add 84 to that and get 94 plus 11i. Interesting. Any question about this one? So in a sense, it's just like multiplying polynomials together, except we have an additional rule that I squared is negative 1. Okay, here's something interesting. What if we do 2 plus 7i, and we multiply it by 2 minus 7i? So, yes, let's look at these. These two numbers are special with respect to each other. They're a special pair. 2 plus 7i and 2 minus 7i, how are they special to each other? They're conjugates, right? And we're computing their product. So let's watch what happens when you compute the product of complex conjugates. Well, the F term would be 4. The O term would be minus 14i. The I term would add 14i. And the L term would subtract 49i squared. So notice that the product of conjugates still causes the middle things to cancel, right? Negative 14i, and then add 14i. So the middle ones, they cancel. And what do we do with the I squared? It becomes negative 1. So this would be 4. 4, and then minus 49 times negative 1. So that'd be 53. And what I want you to observe is that 53, that's real. So we multiplied two complex numbers and got a real number. Okay, so now we have enough time to start the next thing. So I need to do that. Fine. What if we wanted to do 2 plus 7i divided by 5 minus 12i? Now we want to divide two complex numbers. Well, here's the difficulty, the problem that we need to overcome. We need the denominator to be real, but it is currently complex. Okay, let's think about it for a moment. So we want to take this expression that was given, and the only thing that's permissible to multiply this by is 1. You can't multiply it by anything else, because if you multiply it by something and it's not 1, then you change it. It's got to be 1. Also, the problem that we face is that the denominator is not real. But just like when you multiplied these two conjugates and the result became real, if we could somehow multiply the denominator by its conjugate, then it would be real. So what's the conjugate of 5 minus 12i? 5 plus 12i. But what's the cost of putting that 5 plus 12i down there? Also putting it up here. And this red thing, that's altogether just a peculiar way to write 1. And then if you carry out all this arithmetic, then you can get it to be in the form a plus bi. We'll talk more about that next time. We've got to do the quiz. Okay.